Welcome to this lecture on lithography. In the last lecture, we have discussed about the material used for the MEMS fabrication and how wafer is prepared. In this lecture, we will discuss about lithography process. It's a process for transferring the geometric pattern on a mask to a radiation sensitive material that is called resist. The required geometrical pattern of the mask is first prepared in the digital form in a computer program and then on an optically flat glass or quartz plate covered with a thin chromium film known as mask. The opaque portion of the mask is prevent the radiation from reaching the resist on the wafer, and the transparent portion will allow to reach the radiation on the wafer. A mask is used repeatedly to expose the selected region of the resist on a wafer. A single mask can be used again and again for multiple wafers. Lithography, there are four types of lithographies. One is optical lithography, electron beam lithography, X-ray lithography, ion beam lithography. Two types of photoresist we are using here. One is the positive photoresist. In that case, exposed region is removed after developing. And one is negative photoresist, where exposed region will retain after developing. Is optical lithography, where the photoresist, this is substrate, it is a complete full layer of photoresist initially and is exposed with the UV rays through the mask. This is the transparent portion of the mask, this is opaque portion of the mask. After developing in the solution, the exposed area that will be removed from the surface, and this is negative photoresist, where this is substrate, a complete layer of photoresist initially, and it is exposed with the UV rays through the mask. Here the exposed region will be retained after the developing. See, in case of positive photoresist, exposed area will be removed, and in case negative photoresist, exposed region will be retained. Important parameters for the photoresist the optical lithography are: the first, the photoresist, which type of photoresist we are using, negative photoresist, positive photoresist, and which one photoresist we are using. The way of exposure, that is contact printing, proximity printing, or projection printing we are using. Wavelength of the light, what intensity of the light we are using, and width of the features, that is also known as diffraction effects. This is the photoresist, positive and negative photoresist we are using. Its photoresist may be organic, inorganic, or organometallic. Which type of processing we are using, that is E-beam process lithography, ion beam lithography, X-ray, deep UV, mild UV, or near UV. Optical lithography in photoresist properties. In the positive photoresist consists the positive agent and resin, and after developing, the exposed area will be destroyed. It provides the better resolution than negative photoresist. Examples are MP2400, HPR206, deep UV, MPMMA, and polybutane cell phone, etc. In negative photoresist contain photoactive agent plus rubber in place of resin, and after UV exposing, the exposed portion will be less soluble in the developer. It will retain. The problems in the negative photoresist are swelling problem. It will reduce the resolution by 2-3 times of initial thickness. And examples are SU8, Kodak, Micron. Optical lithography steps. First of all, the wafer is placed on a rotating disc that is rotating at the speed of 2000 to 8000. Then a drop of photoresist is placed at the center of the wafer. Because of the rotation, centrifugal force, the liquid photoresist will spread over the wafer, and there will be uniform coating of the photoresist on the substrate. After applying the photoresist, it is pre-baked at a temperature of 75 degrees centigrade to 100 degrees centigrade for about 10 minutes. It will improve the adhesion of the photoresist film to the substrate. and also remove the organic solvent. After pre-baking, next is UV exposure. It is the wafer coated with the photoresist is exposed with the UV rays through a mask. Next step is developing. After UV exposing, what we have to do? For it's developing. It's placed the wafer is placed in a developing solution, where in case of positive photoresist, exposed region will be uh, removed, and in case of negative photoresist, unexposed portion will be removed by the developer. That will for positive photoresist and negative photoresist, different developers are used. A single developer can't be used for positive photoresist. For positive photo, different developer are used, and for negative photoresist, different developers are used. After developing, the next step is post baking. The wafer is placed for at 120 degrees centigrade for about 20 minutes in the oven. It will harden the retained portion of the photoresist. After post baking, etching process, where after developing, the weaker or the soluble photoresist will be removed, and hardened photoresist will remain there, and through that window in the photoresist, the chemical etching chemical will remove the material from the substrate. In case next is after completion of the etching process, the complete photoresist is removed from the surface of the substrate using organic solvent. There are three ways to use the mask over the surface, over the substrate during UV exposure. One is contact printing, next is proximity printing, third one is projection printing. In contact printing, the mask is pressed against the resist with the pressure of 0.05 to 0.3 atmospheric pressure. It's just touching to the surface. This process provides the high resolution that is less than 1 micrometer. The mask here we are using is flexible. It's not hard like glass. It's a flexible like plastic. The problems are, we are just we are just placing the mask against the surface. So there may be some portion it's not touching the surface. There may be gap between the mask and the substrate region. So there will be decrease the resolution, and because of the contact between the resin of resist and that mask, the mask is just damaged. There may be pinholes, scratches, the fractures in the mask or in a pattern on the resist. So it will reduce the life of the mask also. Next is proximity printing, where mask is placed above the photoresist by a distance of 25 to 50 micrometers. It's not touching to the surface. It will increase the life of the mask. There will be no pinholes, no scratches, no fractures, but there will be resolution is not good as contact printing because of the diffractions of the light through the text. Next is projection printing, where complex optics are used for transferring the image from the mask to surface photoresist. Resolution in case of projection printing is very high, more than proximity printing. See, these are diagrams where this is the silicon wafer, photoresist, this is the mask just touching the photoresist, pressed against the photoresist, and it is exposed with the UV rays through the optical system. In case of proximity printing, there is a gap between the photoresist and the mask, and is again exposed with UV rays through optical system. There is no it's not touching, mask is not touching to the photoresist. Third one is projection printing, where this is the substrate with the photoresist This is the mask and this is UV exposure source. Here two optical systems are used for transferring the pattern from the mask to the substrate. Sorry. Next is E-beam lithography, where approximately 10 to 50 kilovolt electron beam is used. There is no need of mask here. It can be used for preparation of the mask. Generally, it's used for preparation of the mask. The resolution is very good. It's less than 1 micron, about 20 nanometer resolution is possible with the E-beam lithography. It's not suitable for high length features. Means the size of the feature is very big, then it's not suitable. It's developed in 1960 by SEM technology. There is link is given for the YouTube that you can go through it and you will learn more about this process. Applications of E-beam lithography are for mask making. All the masks just prepared by the E-beam lithography. For direct writing on the ICs without using of the mask, it can be used. And for research applications, nano manipulators, probe growing, UCNT, fine structures like. Next is Liftoff technique. Here you can see this is the substrate and apply a photoresist here on the substrate. Then it is exposed with the UV rays through the mask. After UV exposure, the exposed area, there it is, this one, these are the exposed area. Okay, these are the opaque part, this is the transparent part in the mask. So these are the exposed area that will be hardened and remaining portion will remain softened. So after developing, the exposed area will retain and remaining will be removed. After development, metal deposition is done, where there is thin layer of metal on the substrate and on the photoresist here. After metal deposition, this portion is removed, it is dissolved in the chemical that includes the metal layer along with photoresist both. So there are the windows in the layer substrate. There is a difference between the Liftoff techniques and the lithography technique. In case of lithography technique, first of all, a thin film of metal is deposited on the substrate. After that, applying the photoresist, exposing it with UV rays, and after developing, it will remove the softened portion of the photoresist, and through that windows, etching process is done to remove the material. In case of Liftoff technique, first photoresist is applied, then expose with UV rays and develop it, and after removing the soft material photoresist, only hard photoresist will be there, and after that metal deposition is done, and after the deposition remove the photoresist and unwanted metal in the solution. See the difference here? Deposition of metal film is done at the starting, and here deposition metal film is done after development of the solution photoresist. Here in the last, etching process is also done. There is no need of etching process. It is removed by the solution directly in the along with photoresist. These are the references. Thank you.